Satellite geodesy is geodesy by means of artificial satellites, the measurement of the form and dimensions of Earth, the location of objects on its surface, and the figure of the Earth's gravity field by means of artificial satellite techniques. It belongs to the broader field of space geodesy. Traditional astronomical geodesy is not commonly considered a part of satellite geodesy, although there is considerable overlap between the techniques. Satellite geodetic data and methods can be applied to diverse fields such as navigation, hydrography, oceanography, and geophysics. Satellite geodesy relies heavily on orbital mechanics. Satellite geodesy began shortly after the launch of Sputnik in 1957. Observations of Explorer 1 and Sputnik 2 in 1958 allowed for an accurate determination of Earth's flattening. The 1960s saw the launch of the Doppler satellite Transit 1B and the balloon satellites ECO 1, ECHO 2, and PAGEOS. The first dedicated geodetic satellite was ANA 1B, a collaborative effort between NASA, the DoD, and other civilian agencies. ANA 1B carried the first of the U.S. Army's SECOR instruments. These missions led to the accurate determination of the leading spherical harmonic coefficients of the geopotential, the general shape of the geoid, and linked the world's geodetic datums. Soviet military satellites undertook geodesic missions to assist in ICBM targeting in the late 1960s and early 1970s. The transit satellite system was used extensively for Doppler surveying, navigation, and positioning. Observations of satellites in the 1970s by worldwide triangulation networks allowed for the establishment of the World Geodetic System. The development of GPS by the United States in the 1980s allowed for precise navigation and positioning, and soon became a standard tool in surveying. In the 1980s and 1990s, satellite geodesy began to be used for monitoring of geodynamic phenomena, such as crustal motion, Earth rotation, and polar motion. The 1990s were focused on the development of permanent geodetic networks and reference frames. Dedicated satellites were launched to measure Earth's gravity field in the 2000s, such as CHAMP, GRACE, and GOES, or use its instruments to track, or be tracked by another's satellite. Global navigation satellite systems are dedicated radio positioning services, which can locate a receiver to within a few meters. The most prominent system, GPS, consists of a constellation of 31 satellites in high, 12-hour circular orbits, distributed in 6 planes with 55 circumflex degrees inclinations. The principle of location is based on trilateration. Each satellite transmits a precise ephemeris with information on its own position, and a message containing the exact time of transmission. The receiver compares this time of transmission with its own clock at the time of reception, and multiplies the difference by the speed of light to obtain a pseudo-range. 4 pseudo-ranges are needed to obtain the precise time, and the receiver's position within a few meters. More sophisticated methods, such as real-time kinematic, can yield positions to within a few millimeters. In geodesy, GNSS is used as an economical tool for surveying and time transfer. It is also used for monitoring Earth's rotation, polar motion, and crustal dynamics. The presence of the GPS signal in space also makes it suitable for orbit determination and satellite-to-satellite tracking. In satellite laser ranging, a global network of observation stations measure the round-trip time of flight of ultra-short pulses of light to satellites equipped with retroreflectors. This provides instantaneous range measurements of millimeter-level precision which can be accumulated to provide accurate orbit parameters, gravity field parameters, Earth rotation parameters, tidal Earth's deformations, coordinates and velocities of SLR stations, and other substantial geodetic data. Satellite laser ranging is a proven geodetic technique with significant potential for important contributions to scientific studies of the Earth/atmosphere/ocean system. It is the most accurate technique currently available to determine the geocentric position of an Earth satellite, allowing for the precise calibration of radar altimeters and separation of long-term instrumentation drift from secular changes in ocean surface topography. Satellite laser ranging contributes to the definition of the international terrestrial reference frames by providing the information about the scale and the origin of the reference frame, the so-called geocenter coordinates.